तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last few classes, we have been talking about finding the integral of a function numerically. So, today we will discuss finding the solution of a differential equation. So, what you mean by that is that if you have an equation of the form that is dy, a simple equation of this form, that dy by dx is equal to f of x, and you want to find out the solution to this. What I mean by that is to find out what is y as a function of x. Okay, so that is what we want to do. So, okay, so now this is a simple ordinary differential equation of order 1. So, in general we could have a differential equation of this form d to the power n, that is dxn, that is the nth order differential, the nth order derivative equal to some function of the derivative of order n minus 1 to so that is dy dx d squared y by dx squared is a function of all of this, and d n minus 1 y by dx n minus 1 y x. Okay, so in general it could be a function of all of this quantity. So, now we want to solve this equation, which means that we want to find out what is y of x and what is y dy by dx as a function of x, and d squared y by dx squared as a function of x, etc., all the way up to d n minus 1 y by dx to the power n minus 1, so that as a function of x. So, find all these quantities, okay, and also y of x, and all its derivatives. Okay, so, if you solve this equation, what you mean by solution would be that to find all these quantities. Okay, so that is what we mean by solving a differential equation, and there are many ways of doing this. Now, what we are interested here is to find the use some numerical methods of solving such differential equations, such ordinary differential equations. So, ordinary in the sense these are functions of one variable. Okay, so, there is only derivative with respect to x, so ordinary differential equation as opposed to partial differential equations. And the right hand side of this function could be linear or non-linear. Okay, so, methods are general for this. So, it could be a linear function, or it could be a non-linear function. It could be a function of x and y, or x squared, y squared, or any powers of x, or any non-linear function of x and y on the right hand side. So, it could be a function of x and y. So, to start with, we would look at simple equations of this form, that is first order differential equation. So, the power on this tells us the order of the differential equation. So, this is a first order differential equation, and we will start with that, the first order differential equations, and we will see that all higher order differential equations can in turn be written as a series of first order differential equations. So, numerically it is enough to know a method to solve first order ordinary differential equation, and then we can generalize that to higher order equations. So, that is what we would be looking at. Okay, so, it summarized, so this is what we wanted to do, that we will look at some methods of solving ordinary differential equations. So, today's lecture we will look at a few methods to solve ordinary differential equations. So now, as I said that we were looking at first order equations to start with. Okay. So now how do we solve this? To solve that we need boundary conditions to be specified. Okay. So now that is another criteria. So now if you have a differential equation of this form, then you would say it is an nth order differential equation. So now to solve nth order differential equation, we need n boundary conditions. Okay. So boundary conditions are the value of the function y and its derivatives specified at the boundaries. Okay. So we need that to solve these equations. Okay. So if you want to solve an nth order differential equation, we need n boundary conditions. So here, for example, we need one boundary condition. So you could have, so we want to go in this solution has to be written from some starting x value to some ending x value. So x0 to some x1. Okay, that's what you would be solving these equations for. Okay, so you have to solve all this equation from some starting x value to some end x value. And now, if some of these conditions are specified, boundary conditions are the values of this, it has to be specified. So some conditions can be specified at the beginning, and some specific conditions can be specified at the end. That is, for example, we want to know what is y of x at starting from x equal to x0 to x equal to x1, let us say. Okay. And then some of the boundary conditions can be specified at x0 and some can be at x1. Right. So in general, when you solve an nth order equation of this type, and if all the boundary conditions, that is n boundary conditions, are specified at x equal to x0, that is the beginning value, the starting value, then we call that an initial value problem. Okay. And if some of them are specified here and some of them are specified at the other end, then we would call that a boundary value problem. Okay. So there are two different kinds of differential equations, of ordinary differential equations. Then the methods which we adopt for this are slightly different. So you could have repeat that all the boundary conditions specified at x equal to x0, and then it is an initial value problem. And if some are specified here and some are specified at the other end, then it is called a boundary value problem. Right. So what we are looking at in this few lectures would be the boundary value, sorry, the initial value problem. That is, all the boundary conditions are specified here at the beginning. That is the initial value problem. That is what we will be looking at. Okay. So it is summarized here. So we need to solve a differential equation of order n, we need n boundary conditions. Right. So now, if all the boundary conditions are specified at one point, that is at in a starting value. Okay. Of course, it is not necessary that the starting value has to be a higher value of x than the other one. It can be anywhere, but one point where we start the integration, and that point, if all the values are specified, then it is called an initial value problem. If m of the boundary conditions are specified at the starting value x equal to x0, and then the rest of them, that n minus m, that n is the order of the equation, the other boundary, then it is called a boundary value problem. Okay. So I guess this is clear. So what we will be looking at in this few lectures would be solving equations of this form, that is general nth order ordinary differential equations, linear and nonlinear, okay, with all the boundary conditions specified at x equal to x0. Okay. So we will have the boundary conditions. In this particular case, the boundary conditions would be when you want to solve this equation, the boundary conditions are, so we call them as boundary conditions BC. So boundary conditions should be y at x0, right, and y prime at x0. So what do you mean by y prime is the first derivative of y, and y double prime at x0 all the way up to y n minus 1 prime at x0. So this has to be specified to solve this equation as an initial value problem. Okay. So we are starting from x0 to x1. So all the values of the function and its derivatives are specified at x equal to x0. Okay. So we need that. That boundary condition is required to. So there are n boundary conditions here to give. Okay. Now this is a notation which you are going to adopt. that is prime means derivative with respect to x, and for higher order derivatives we will put them in bracket. If a power is put in bracket, that means its derivative that many times. Okay, so this is the n minus 1th derivative of the function y evaluated at x equal to x0. So that is a notation which you are going to follow. Okay, so in the past few lectures we had seen very simple ways, some ways of integrating a function. So we can use something similar, okay, to find the solutions of a differential equation too. Okay, so we will start with a very simple scheme to solve an equation of this type. Okay. So let's stick to the first order equations. So for the time being we are going to stick to first order equations, and then we will come to the higher order equations later. Okay. So we are going to solve equations of this form, y of dy by dx is equal to f of x0, by using some simple schemes, okay, for solving equations to start with, and we will go to little more sophisticated schemes in the coming lectures. Okay. Sophisticated but more accurate and faster. So here, so what we want to find is y of x at all values of x starting from x0 to x1, and we are given y of x0 as y0. Okay, now that's a boundary condition given to us. The boundary condition is y of x0 at equal y at x0 is y0. We need only one boundary condition because it's a first order equation. So how do we solve such an equation? So that's I said dy by dx is now written as y primed, right, and f and the right hand side is a function of x and y. Okay. So we will start with an equation of this form. Okay. So now we need to discretize this function. Okay. So that is all numerical methods for solving differential equations require that. That is just like what we did for the case of integration. We need to discretize this function, that is evaluate this function at discrete values of at a set of values of xn and yn, not necessarily equally spaced, but some discrete values of xn and yn. So what is again the notation, please note the notation is when I say yn, it is y at x of n, xn. Okay, so what we are going to do is we are going to split this interval x0 to x1 as xi. Okay, so we have x values as x0, x1 up to xn. Okay, so xn being equal to x. Okay, so whatever the end value is. Okay, let's say x equal to x0 to x start to x end. Okay, so that has been split into n different values, and what we call as yn is y of xn. Okay, so y evaluated at xn is y of n. So that's what we want to solve, and what we know is y0, which is y at x0. Okay, that's what we start with. Okay, and then I can write this function and this derivative, this equation. I can solve this, okay, and say that I can solve it like this. I say y at x0 plus h. Sorry. So the method is very simple. That is, we start with saying y at x0, which we know, and x0 plus another value h, that is equal to y of x0 plus, right, dy by dx at x0, the Taylor series expansion into h, and something of the order d squared y by dx squared, that is y double primed, which is left out, into h square, right. So something of the order y double prime into h square is left out. Okay, so that's the error in this approximation. Okay, so now this looks familiar. Okay, so now we know what dy by dx is, and that's f of xy. So I can write this as y at x0 plus f of xy at x0, right? That is y0 into h. Now h is the interval between distance between x0 and x1. So in general, I can write this as yi plus 1 is equal to yi plus f at xi yi into h. Okay, so I hope that's clear that we have we can take any point and then Taylor expand around that point and cut off the series at the first derivative, and then I have an error of the order h square, h being the distance between x0 and x, and the next sum which we have taken is discretized here. And then I can say that y at x0, y of x0 plus h is y of x0 plus y of x1 and y evaluated at x0, y of x0 into h. This is a function of that because dy by dx is f. Okay, so in general I can do this expansion around any point. So if I know the xi value, y at xi, and then I can find y at xi plus 1, which is y xi plus h, which is yi plus 1, right. So let me write this again. So that is this is the same as writing y at xi plus h equal to y at xi. The notation is y at xi plus f of xi y at xi, right. Okay, so now this is the same as that. So this is a general formula which you are going to use. Okay, so if I know y at I equal to 0, or right, then I can y 0. If I y y 0, and then I can continue and build up the function value, the y value as we go along. Okay. So the idea is that we start from some point, that is the initial value which is given to us, right, and then we build up. Okay, and we are using the local tangents. So what we are doing is that you are given x versus y, which you would want to solve for. Okay, and we are given the y value at x equal to x0. Okay, some y value is given. Let's take it as that. Okay, and then we are given the local slope, right? That's the derivative, and then we use that, and then use that we know the slope, so we go there. Okay, using that slope, and then we know the slope at that point, and so we keep going in some using some interval. Okay, so that's the general scheme. So we can do this. This way we can find out all the points of that function or y of x. We can so that's let me summarize that again here. Okay, so that's called the Euler's method. Okay, so now what we just described is called the Euler's method, the simplest way to solve an ordinary differential equation of order 1. So that's the following, that we write the point notation xi plus 1 equal to xi plus h, and we will Taylor expand y of x around that point, and we write as y of xi plus h as y of xi plus h f of xi yi. Okay, now, so once we have that, and then we start with y of x0, and then we keep building the functions one after the other at different points in a serial manner. So we will write it as yn plus 1 is yn plus h into f of x and yn, okay, plus some error term which is the order h square y double prime at evaluated at some using mean value theorem. Okay, so now this is, as you can see, it's extremely easy to program, okay, but not quite accurate. Okay, and we would need to use extremely small intervals of h to actually get this function value. Okay, we want to use very small intervals of h to get the accurate results for using this particular method. Okay, so we will just see this in a program. Okay, it's very easy to program, so we will as well program this. Okay, so it will be called Euler's method. Okay, so the program is similar to the integration program which we had seen in earlier lectures. That is, we need an upper limit and a lower limit, right, and we need to tabulate the function at the x values. Okay, and we need, our idea is to obtain the y values. Okay, so that's what the summary is. Okay, we have the x values tabulated between the limits x0, that is upper limit, and the lower limit. Okay, and the y values, we need to get the y value. So x and y are pointers here. Okay, so now we first give some allocate some memory to those points x and y, and then we can put in the x values. Okay, so we put in the x values here. Okay, so now with the lower limit at equal intervals. Okay, so it's exactly same as what we did for integration in the last class. So, we have the x of I given by lower limit plus I into xp being the interval what is called h in the discussion just now. So, this is the tabulated values of x we have obtained. So, now we have a boundary condition. So, now we are trying to solve. Now, what are we trying to solve? We are trying to solve an equation of this form. So, let us say we want to solve. So, we are trying to solve y prime is equal to minus 2y. That is what we are trying to solve. Dy by dx is equal to minus 2y. That is a equation which we are trying to solve. And with the boundary condition that y of 0, y at x equal to 0, that is y at x equal to 0 is equal to 1. That is our boundary condition. So, we know what the solution to this is analytically. So, we can compare that. The solution would be, we know that y of x is equal to exponential minus 2x. Right. So, that will be the solution to this equation, we know that. So, which satisfies the boundary condition that y at x equal to 0 is 1. So, now we can solve this numerically, that is what and compare this result. So, we are using Euler's method, remember. So, my boundary condition is y of 0 is 1, right, and then I go from 0 to n points minus 1, that is the interval. N points is the number of intervals I have going to give, which is read off here. So, it would read off here. It will ask you how many points you want to put in between x upper limit and lower limit, and then it reads that off on the screen. And I have allocated memory according to how many points I want it. So, x and y, and then I divided my interval to n points by using this, where xp is actually upper limit minus lower limit divided by n points, that is the interval. And then I tabulated all the x values, and then I go here and say that y at I plus 1, it is equal intervals. So, y at I plus 1 is yi plus the derivative. So, the derivative function f is yi. So, what we are going to use is this formula, y at I plus 1 is yi plus f into h. So, f is minus 2y. So, yi minus 2y into h is what we are going to use, and that is what it is here. And we will just print out this, and we know the actual solution. So, let us just run this and then see what would we get. So, this is Euler method. So, we will run this program, and so we will just run it for, let us say, about 20 points in between 0 and 2, that is each interval being 0.1, h being 0.1. So, then we will plot that thing which you. So, the program we are writing the result into a file called Euler solution dot dat, that is where I am writing the xi and yi's. I am writing that into this file. So, we can plot that value. So, with actually we will plot this Euler solution dot dat. So, here is my plot of the Euler solution, and we will compare that with the actual solution, that is we know that it is exponential of minus 2 star 2.0 star x. So, that is our actual solution, we know that. So, we will just compare that with this. So, that is what we get. So, we can see the solution, this asterisk which we see here is the points which we obtain using this Euler scheme, and the green line which we see here is the one which we obtain the actual solution is, the real solution is exponential minus 2x is that way. So, we have used 20 points to evaluate this integral, and you can see that we are not quite onto the line. We are off here by this point. So, let us see how many points we would require to get to that actual value. So, we can run this program again use here. and now let us run it with some 50 points in between, and then go back and plot that thing again. Okay, so now we increase the number of points. Okay, so we are getting better. So you can see that as we increase the number of points, we go more and more close to the actual solution. But we need to have a large number of points. So we use 50 points between 0 and 2 to get at a reasonable accuracy here. Okay, so it of course depends on what accuracy you need to get, but you can see that this simple method is not quite accurate. We need a large number of function evaluation at very small intervals, which can lead to other problems like round off errors, etc. in other computation. Okay, we are using this as part of some other computation. So this large number of function evaluation at small intervals could also lead to other numerical errors creeping in. Okay, so even though extremely simple, Euler method is not quite efficient. So we will try to improve this method slightly. We will try to devise a scheme which would improve it around this simple scheme. Okay, and that's what we call the predictor corrector method. The next method, okay, which is called the predictor corrector method. So this isn't very different from the Euler scheme. It's just using the Euler scheme, but now we do an iterative scheme which involves 2 steps. So the first step, we would evaluate just like in the Euler scheme, y at xi plus h, that is yi plus 1, as y at xi plus h times f of xi yi. Okay, so that's the Euler scheme, right? You can see. And now we call that as the predictor equation. Okay, so that predicts what is the y value at xi plus h. So to distinguish it from the true solution, we put a simple y0 here. Okay, so this doesn't mean that it is a 0th derivative. It just y0, just to show that it is a predictor. Okay, it's not the actual solution. Okay, so then the corrector. Okay, the corrector is that when what we do is, now instead of using just one derivative of the function at xi yi, now we will use an average derivative of the function at the one is the initial value and other is the predicted value, and then use that average value as the derivative and get the corrected y of xi plus h. So graphically this means the following. So let me just write that down here. So we are doing the same problem, so with the boundary condition, initial conditions, etc. given. Okay, and then what we are going to do is, okay, so now what we are going to do is to write yi plus 1, okay, as I said, a predictor, which is yi plus the function value at xi yi into h. Okay, so function being the derivative. So now that's like saying that, and then I use this quantity, okay, this is yi plus 1, and evaluate the derivative at that point yi plus 1. Okay, so graphically it's something like this. So this is my y and this is my x axis. I start from somewhere here. Okay, I have my slope there. Okay, now the slope is, let's say, like this. Okay, and then that's my distance h. Okay, so I go to this point. Okay, using that slope along the slope, right? So I start from here and I go to along using that slope. Along the slope, I go to this point, okay, by using this predictor scheme. Okay, and then I evaluate the slope there. So I would now, the next step would be after this will be to evaluate y f at xi plus h, comma yi plus 1 0. Okay, so I will evaluate it at that point. Okay, so that's what I will do. Okay, and then that's evaluating the slope at this point. And then I would take, so now let's say the slope is somewhat like this. Okay, at this point the slope is like that. Okay, then I take this function value, the slope here and the slope here. Okay, and take the average of that slope. Okay, and the average of that slope. Okay, and then use that to go from here to here. So I will replace this segment here by an average slope which I get, which will be now like that. Okay, so okay, let me draw this a little bigger. Okay, so I go to this point and then I choose. So this is a slope at that point. Okay, so then I would have an average slope which is like that. Okay, so then I use that average slope to go to the next point. Okay, that's what the scheme is. That's the corrector scheme, is to say that yi plus 1, actual yi plus 1 is then equal to yi plus the, so let me call this as the two functions. So it is h by 2 now at f value evaluated at xi yi and plus f value evaluated at xi plus 1 f value evaluated at xi plus 1 comma yi plus 1 0. Okay, so now use this average value to go to that thing. So now this may not give me the correct answer, right? So maybe there will be a difference between this predicted value and a corrected value. Okay, then what I do is I will again go back here. Okay, I will now substitute my yi plus 1 0 as yi plus 1 obtained from here. Okay, so now the step is the following. I start from here, okay, and then evaluate this function here, right? That is the derivative at xi plus h yi plus 1. Okay, and then I use that average derivative to compute yi plus 1. Okay, and now if there is a difference between yi plus 1 and yi plus 1 0, then I will replace yi plus 1 0 by yi plus 1, and I go back here again, okay, and again compute this, again come back here and check is there a difference between yi plus 1 and yi plus 1 0. Okay. So I do this iteration again and again till the difference vanishes, the difference between yi plus 1 and yi, or I can define an error epsilon as yi plus 1 minus. So okay, let me do the next step would be to actually look at the difference, that is epsilon as yi plus 1 minus yi plus 1 0 divided by yi plus 1 and mod of that. Okay. So now if epsilon is not equal to 0, and then I will go back as it's saying that yi plus 1 is 0 is yi plus 1, and then I go back from here to here again. Okay, so that's what I would do. Okay, so I'll start from here and evaluate yi plus 1 using this mean derivative, and I look at the difference, and if it doesn't, if the difference is not, if this epsilon is not satisfactorily 0, it's something less than the predetermined value, and then I'll replace yi plus 0 by yi plus 1 and go back here and then again do the step till this epsilon is sufficiently small. So now this method is called the predictor corrector method. Okay, so we can see this, how this would improve the simple Euler scheme of just doing this once. Okay. And you could have a simple predictor corrector method also, just do this once and then do this once again. Okay, that's another scheme, but the iterative scheme would be to do this repeatedly till we get yi plus 1, till the epsilon below some predetermined accuracy. So smaller than a predetermined error, or to satisfies our accuracy condition. Okay, so we will look at that implementation of this now. So here is a code which would which implements it. Okay, so that's a predictor corrector code, and then again earlier the part of the thing is same, and you have the x values and the y values in the upper limit, etc. specified. Okay, now this S modified this program says that it's a little more general. So I have some subroutine here or a function here which I call the function. So this subroutine will actually returns to me every time I call this one, returns with the arguments, it will return to me the function values and its derivative values at that point. So I have defined some more arrays here, which is xx, yy, dy dx and dy dx1. Okay, and so that is so these are derivatives. Okay, so now I have defined two derivatives here because I want to distinguish between the actual the derivative at xi yi and this is the derivative at xi plus 1 yi plus 1 predicted values. Okay, so that is dy dx and dy dx1, the two derivatives. Okay, and this is the value at which we are going to evaluate the function xx and yy, that is xi and yi. So then, okay, we allocate some memory here using the malloc functions for the x and y as before, and we also allocate memory now to the xx, yy and dy dx, dy dx1, etc. Okay, so we need that. Okay, and then we will compute this. Now what we do is, again, we have an initial condition. We have divided the interval between the upper limit and the lower limit by n points. Okay, so that is xp is the interval and equal intervals. Okay, and I've tabulated the function the function values into this array. So the x values into this array called xi in the equal intervals of xp. So now we start with the boundary condition, which is y of 0 is 1. Right. So now we will do that. So we will first write this x of 0, y of 0. That's our initial value, which is given to us. That's returned to this file called predictor corrector solution.dat. Okay, and now we will write all the solutions into this particular file. Okay, so now I start with an error equal to 1. So I want to do this solution at every point, starting from 1, I equal to 1. Right. So at every I plus 1 point, I need to solve this. Okay, so I start the first point. So I put the error equal to 1. Okay, and I am doing the xx and yy at x of I and y of I, that is x of 0, y of 0. That's the starting values. Now I evaluate the function here. Right. I evaluate the function here. So I will get the derivative at that point. So if I pass to this function the x value and the y value, it returns the derivative. So this is general. So if I want to do this program for a different differential equation, right now I am doing it for dy by dx is equal to minus 2y, but I can do this for a different differential equation. In that case, I would have to replace this function. So this function here is simply returning a minus 2y. So remember, these are all of them are pointers. So I have written them as that's why this asterisk signs come in here. Okay, so it's dy by dx is minus 2y. That's what it returns. Okay. Okay, so I'll start with that. So then I have my predictor equation here. So before everything is starting, so in this loop, so for this particular I value, given that I value, I can compute the next y value at the next point, that yn is y next, that is y at I plus 1, predicted value, that is yi plus the interval multiplied by the derivative. Okay, the derivative is returned by this function dy dx 1. So I have the function value returned there, correct. Okay, so then I now go into the corrector loop. Okay, now this is my corrector loop. So this has been predicted. Okay, and then I go into a corrector loop, and the corrector loop operates till my error is less than 10 to the power of minus 4. Okay. So that's the scheme here. Okay, so this is my predictor. Okay, so I just predicted the value. The next value is yn is equal to yi plus xp times dy dx. Okay, and then I go into do the corrector here. So that is xx now is xi plus 1, so next value, and y is yn, the next value, and then I call the function again and I get the derivative here. Right, so now I got this derivative, and then I go to the next function value. Now this is a corrected function value, which is the y of I plus the average of these two derivatives. Okay, that is y dy dx plus dy dx 1 by 2. So remember, dy dx is evaluated at I plus 1 and the predicted y value, and this is evaluated at I and y of I. Then I compute the error here, okay, as yi plus 1 minus yi divided by yi, the absolute value of that. Okay, and then I put the y next. Now the next predicted value as this value which you obtain from here is the next predicted value, and we will continue this loop till this error is less than 10 to the power of minus 4. So let us run this program here again. So I would run this as okay, so now we will run this program. We will run it again with 10 points. Okay, so let us run it with 10 points. Okay, and okay, so now that's now I am just plotting what you get from the predictor corrector alone, and we will compare that with the value which we get we'll compare that with the actual value. So the green line here is the value which is obtained from exponential minus 2x. That's the real solution, and the red squares here are the one which obtained from the predictor corrector equation. So, you can see that this accuracy is pretty high, that is just use 10 points and we can get this accuracy. Remember, in the Euler scheme, a simple Euler scheme, we need to go to very large values of points. That's we have to use 50 points to get this kind of accuracy. So, the predictor corrector scheme definitely is much better compared to the Euler scheme, but here again we are doing this similar technique, that is we are actually evaluating the function value at many times to get the correct solution. Okay. So, even though we have used only 10 points, but we evaluated the function points at function values at different at many times in each of this corrector loop. In this corrector loop, we evaluated many times to get the correct results. So, it could also have same type of numerical accuracy problem due to round off errors as that in the Euler scheme, but this is definitely much better scheme than a simple Euler scheme. Okay. So, we will go now to a slightly more sophisticated way of doing this, that is using what is called the Runge-Kutta scheme. Okay. So, now this is again a general method for solving first order differential equations, initial value problems. Okay. So, this method is specifically for first order initial value problems, and higher order derivatives can of course be split into the higher order differential equations can be split into first order equations, and the same method can be used to solve them. Okay. So, it is we will just concentrate on the first order equation here. So, that definitely provides much greater accuracy, and now so at the same time we will not do any higher derivatives or something. So, we just again going to use something similar to this. We only work with the first order derivatives, that is to evaluate the function value at I plus 1. I will be using only first order derivatives. Of course, we can ask what the point here is that you can improve the accuracy of this method by going to higher order derivatives of the function, which may not be available to us. Okay. So, we may have to compute them numerically, etc., but we will not do that. Okay. We will just stick to this first order derivative and then try to improve the accuracy of this scheme. So, that is one of those methods, is this what this Runge-Kutta method is. Now, there are different orders of Runge-Kutta. So, we will be first looking at a second order Runge-Kutta to actually explain the basics idea behind this method. Okay. And then, but normally in all the standard routines which you would see, they will be using a fourth order Runge-Kutta. I will just explain what that means actually is in a few minutes. So, let us look at a differential equation of this form as we have been doing there, and then write the solution in this form. Okay. So, that is we will write the solution, that is y n plus 1 as y n plus a k 1 plus b k 2. Okay. So, that is a basic idea of the Runge-Kutta scheme. So, we want to write the solution, that is y at n plus 1, that is y n plus 1 is y x n plus h as y n plus some coefficient times a function k 1 plus another coefficient times a function k 2. So, in the case where k 2 is equal to 0 and k 1 equal to f of x n y n, we are back to the Euler scheme, which is right. So, that is the Euler scheme. Okay. So, that is this method is, okay, you can see, is the generalization about that, k 1 equal to this and a equal to h, k or a equal to 1 and k 1 equal to h times f of x and y n, it gives us the Euler scheme. So, we want to write this slightly differently. We want to say that this is k 1 is h times f of x and y n. Okay. So, we are going to write this in this fashion, that k 1 is h times f of x and y n, and we say k 2 is h times f of x n. We were going to write k, okay. So, write x n plus h comma y n plus beta times k 1. Okay. So, that is what we want to write. Okay. So, alpha times x, sorry. So, x n times x n into xn plus alpha times h, and then yn plus beta times k1. Okay, that's the scheme which we are going to use. Okay, and then our idea would be to determine this alpha, beta, and a and b. Okay, so remember, in the limit a goes to 1, b goes to 0. Okay, a goes to 1 or b goes to 0. Okay, that's enough. Then we don't have to determine k2. So and then k1 equal to h times f all xn yn. It's Euler scheme, or that is equivalent to saying that alpha is 1, a is 1, and b is 0. Okay, so then we have the Euler scheme. Okay, and in the case, the general case with the second order Runge-Kutta. Okay, in the second order Runge-Kutta, so we are going to write yn plus 1, the next value of y, as yn plus a k1 plus b k2, with k1 as a function of this form. H is the interval between xn plus 1 and xn. So remember, h is xn plus 1 minus xn, and then the function value at xn yn, and k2 is h times the function value now evaluated at xn plus alpha h plus yn plus beta k1. Okay. So again, you can see that for choose appropriate value of alpha, beta, a and b, we can even recover the predictor character from this. So we are only evaluating the first derivatives. Okay, we are not going to any higher order derivatives. Okay. So now the question is, what is the scheme? What is the a, b, alpha, beta is? So now we have to determine these quantities such that this gives you the correct solution of good accuracy. Okay, that's a scheme which we have to do. We have to find out. Okay, how do we determine a, b, alpha, and beta? So what we do is we Taylor expand the function y at xn plus 1. That is what we call the yn plus 1. Okay, we will Taylor expand that function. Okay, so we will do that here. Okay, so what we are going to do is we are going to write y at n plus 1, okay, as yn plus yn prime. Okay, that is derivative evaluated at that function times h, right, and then we can write as yn double primed at h squared by 2, etc. Right. So now yn primed is f and yn double primed. So y primed is f, the function f. So y double primed is this is function of x and y. This one is okay. So we have two terms. One is f x, that is the derivative of this function with respect to x, and other term would be f times f y. Right. So that I'm going to write this as y double prime as f prime as del f by del x. That's what I call one, and del f by del y into del y by del x. F is a function of both x and y. Remember, right? So that is now f x is a notation for that, and this notation is f y, and that is f. Okay, so I have these two terms. Okay, so I can substitute that here. Okay, and then I have some order h cube term. Okay, in this equation. So I can write this as the order up to order h square would be yn plus 1 as yn plus f times yn primed is f, that is h, plus fx plus fy into f times h squared by 2. Now similarly I can write the next term, which is be of the order h cube term. Okay, so that's been summarized here. So you can write this in a Taylor expansion, and I can have the order h square term and order h cube term. Okay, so the order h square term is this one, that is y and hf plus h square by 2, and then I can again find the derivative of this with respect to x. So I get a second derivative of f with respect to x, and then I have the derivatives of these terms. I have second derivative of this with respect to x, that is fx, and then I have fx fxy into f, right, and similarly this expansion. So I have to find the derivatives this for the third derivative. Okay, so that gives us a more complicated equation here. Fxx 2 f, so it will be 1 2 3 4 5 terms. So you can do this yourself. Okay, and then what we can do is, so we have this equation here. Okay, so now let's keep this equation here. Okay, some terms of the order h cube. Okay. And then what we can do is we can take this k2 terms. Okay. Now, so we have this yn plus 1 here, and then what we do is we will expand this k2 terms around x and yn, right, and substitute that here, okay, and then compare these two equations. Okay. So now this is a simple Taylor expansion of this function at this yn plus 1, okay, and then I will now similarly expand this equation by expanding k2 around that point. Okay. So let us do that here. So k2, remember, is so we have this equation with k2 given as h into f of at x plus alpha h comma y plus beta k1. Okay, so now I can expand this and then write this as h times f at x comma y, that is f. So f at x comma y I call this f. Okay, so that is f plus fx del f by del x, that is fx times alpha h plus fy times beta k1, right, that I am expanding around x and y. Okay. And then I have the second derivatives, that is I would have this second derivative function, so that will have f x at alpha h squared by 2 and then higher terms. Okay. So I can write it is in the full series, so I would get a series like that. Okay. So I can expand this k2 around the whole function value in this fashion. So I have beta k, so f of x1 yn, that is what I call f, right, and then I have the next term, that is the derivative of this function with respect to x into alpha h, and then derivative of this function with respect to y into beta k1, and then derivative is the second derivative of this function with respect to x, it's alpha square h square by 2, okay, and then derivative of this second derivative of this function with respect to y, that is fyy into beta square k1 square by 2, and the cross derivative which is alpha h beta k1 fxy. So that is all I have written here. To complete that, that is fyy into beta k1 whole square by 2, and then I have two cross derivatives, that is fxy, that is derivative of this function with respect to x and y, and multiplied by alpha h beta k1, okay, and then higher terms. Okay. So that is what I have. Okay. So now what I will do is, now I have this equation, I can substitute that here, right. So then I will get yn plus 1, now from this as yn, that is, and plus a k1 is just f. So remember k1 was just h times f, so I have a h f because k1 is h times f, and plus b times k2, now k2 is this, so b times h f plus alpha h into f x plus alpha plus beta k1 into fy plus alpha square h squared by 2 times fxx plus beta squared k1 squared by 2 times fyy plus alpha beta hf. Okay, so k1 is f, sorry, k1 is just f, so I can write that as f there. Okay, so this is f times fy, k1 is f, so f times so beta h, so now this term, that is alpha beta h, k1 is f into fxy. Okay, so higher order terms. Okay, so now I have one equation which comes straight from the Taylor expansion of yn plus 1, okay, and then I have another equation which comes from the Taylor expansion of k2, which is f at x plus alpha h plus y plus beta k1. Okay. So now I get these two equations, so equation 1 and 2, and I compare these two equations. Okay. So I compare this equation with respect to this equation. Okay. So I will have to compare this equation which I obtained, equation number 1, okay, which I can write here again. So and then I have the equation which I obtained from n plus 1, okay, this equation. Okay, now I have to compare this one with this one. So let me write this equation here again. So this is one equation number 1, and another equation would be obtained from that as yn plus 1 is equal to yn plus f times h plus fx plus f times fy times h squared by 2, okay, plus higher order terms. Okay, so I can compare order h terms with this and order h square terms here. Okay, so I have order h squared. I compare all the order h and order h square terms between these two equations 1 and 2. Okay, so remember this comes from the expansion of the k2 term here, and this equation comes straight from the Taylor expansion of yn plus 1 around yn, and I can compare these two terms and then fix the value of an alpha such that these two equations are the same. Okay, so that is what the method is basically. Okay, so I can compare, I can write this equation in this form of order h square and order h, okay, and then I can compare this with the simple Taylor expansion of yn plus 1. So this equation actually comes from the expansion of k2. Okay. So if I do that, and I would get the following equations, that a plus b equal to 1, beta alpha and b alpha b beta equal to half. Okay. So now this is the two equations I get. Of course I have 4 unknowns, only 2 equations. So I have some freedom here to choose. So what we will do is we choose a equal to b equal to half and alpha equal to beta equal to 1. Okay, so we'll make a choice like this which satisfies these equations. Okay, and that gives us what's called a second order Runge-Kutta equations. Okay, so we will see the application of this into a simple to solve a differential equation which we just now solved, that is dy by dx equal to minus 2y, and compare that with the other schemes which we had just done. We will and then we will also go into the next order and write down the equation for the next order Runge-Kutta scheme. That is what we will do in the next class.